Okay, so the recording is in progress. I have a TV show called The Sky This Month, and this month, it just got published today. It shows on 66 cable channels around the country. Most of them are in New England. And I also have a YouTube channel for friends and family, such as you all. I have it at the end slide, but it was going to be too crowded to fit it in there. So it's called The Sky This Month, Dave McDonald on YouTube, you can look it up. And we're going to be talking about the August sky and the contents of it and how it works. And one of the things that I probably will remember to mention later is related to how far away are things? Well, the James Webb Space Telescope is up there, operational. We have the first images, and I interviewed Kelly Beatty, who's the senior editor for Sky and Telescope magazine, on the show, and we talked about the James Webb Space Telescope, the recent findings, the images, what they mean, a little deeper. It goes deeper than you might want to, or maybe you want to. So it's a good show, a good interview with Kelly Beatty. And then I talk about the sky in August, which we're going to do. This is like a three-fer, which is cool. We're here for part one, and I'm going to talk to you here about constellations, asterisms, introduction to distances, magnitude scale, colors, the celestial sphere, and what's up there. And then part two, we'll have a 10-minute intermission after part one here. And a 10-minute intermission, we will go into the planetarium theater and see what's up by looking at the dome, and I'll show you the things that I'm going to be talking about in part one. So those of you at home watching by Zoom, you need to come in during the week for the 3 o'clock Tonight Sky Show to kind of get your part two, okay? So you come on in for the 3 o'clock Tonight Sky Show any day during the week for the summer, all right, hey? And then part three is, if it's clear-ish, the New Hampshire Astronomical Society will have a few telescopes outside. So one, we talk about what's going on in August. We'll go in the theater and I'll show you where to find the stuff that's going on in August. In part three, you can actually look at the stuff that's going on in August. So it's kind of really cool. So this is a great Superstellar Friday for you to come to be at. Any questions where we're going? Any answers where we're going? Okay. Very, very good. Okay, so I have a lot of blank slides, just in case I think of something I want to put in later. So constellations. These are prominent summer constellations. Does anybody know what they are? Scorpio and Sagittarius, correct. And so in ancient time, constellations only refer to the brightest stars that appeared to form groups representing mythological figures. We have, in particular, Roman mythology, Greek mythology, and such. And in different cultures around the world, they have their own stories and their own constellations as well. So, when you see here is Pisces the fishies, okay? This is Pegasus the flying horse, which is upside down shown here. But this is an idea of an early map of the sky representing things. Now I mentioned the word asterism, and this is an important word to know, asterism. So what's an asterism? An asterism is a familiar shape which may be made up of stars from the same constellation or different constellations. The Big Dipper is not a constellation.
Say what?
I know. We learned, oh, there's the Big Dipper up there. The Big Dipper is part of the constellation of Ursa Major. Ursa Major is the Big Bear, And the Big Dipper is a part of that. It's an asterism. The Great Square of Pegasus is an asterism, and it actually borrows a star from Andromeda. We'll talk, and I'll show you a little bit about this. So here's the Big Dipper, which is an asterism, right? And so we see it the way it looks, kind of flat up in the sky, but we need to realize that the stars are at varying distances. Now, 5 of them are pretty close to around 80-ish light years away. And I'm going to be using the word and the term light year throughout the presentation from time to time. And what is a light year? A light year is a measure of distance. It's not a measure of time. A light year is how far we go in a year at the speed of light. Light travels 186,282 miles per second. Per second. So, if you can picture Earth, our circumference is in the vicinity of 26,000 miles around, roughly speaking. At the speed of light, you would go around the whole planet Earth at the equator 7.5 times in 1 second. In 1 second, 7.5 times around the equator of Earth. That's moving along. The moon, a good easy to remember number for the distance of the moon is 250,000 miles, 250,000 miles. Now, it ranges from around 239 to 252,000, but easy to remember, 250,000 miles. 1.25 seconds. You go outside with your laser pointer or your flashlight, pointed at the moon, on, bing, it's there. That's how fast light travels. So one of my favorite stars, speaking of distances, is the star here, furthest to the left, called Alkaid. Alkaid is a great star. All the stars are great, but Alkaid's a great star. It's 100 light years away. It's the century star. So when we ever have a century celebration about something, you can take somebody outside and look at that last star, the end star of the handle of the Big Dipper, and say, when this event happened 100 years ago, we're just seeing the light that left that star. The Wright brothers flew their first successful powered flight in 1903, December 17th, 1903. We had a 100-year anniversary here and other places in the world in 2003, 100 years ago. I take people outside, point to the end star of the handle of the Big Dipper and say, see that light you're seeing from that end star? That star's name is Alkaid, and the light, the photons that are reaching your eyes now left that star when the Wright brothers flew. Isn't that cool? The answer is yes. Okay. And then the second one over from the right, that star's name is Dubi, or sometimes pronounced Dubay. It's Arabic, and I'm not a pro at Arabic. Dubi or Dubay. And that star at the end of the Dipper part is about 120-ish light years away. So they're at varying distances, but they appear to be pasted on what was called the celestial sphere. And ancients just thought everything was at the same distance, and there's just kind of on that sky a certain distance away, and they're just all there the same distance. Well, we know now that's not the truth. So the constellations appear, the stars appear to be close to one another, but they're really far away. a demonstration that I have done before with elementary school kids is I give them a pole, 4-foot pole with a star on it, and we kind of arrange the direction and the distance, like in a room like this or outside in a parking lot or a field is better. And we put them so that when you're standing here and you look at the stars, oh, you see the Big Dipper. But now let's pretend we're in a spaceship and let's take a walk. And oh my goodness, it looks different over here because the star's there, and the star's over here. Oh, there's a star behind me. So we can illustrate the three-dimensional aspects of what space really is like. So what we have here is a projection effect, but the stars are not very close to each other at all. Very distant distances. And remember, is the Big Dipper a constellation? No. It's a what? It's an asterism, correct. So I mentioned to you Pegasus and Andromeda, and the Great Square of Pegasus is illustrated here. And notice these zigzag boundaries. You would like to think, you know, United States has places where, you know, you've got Colorado and Wyoming, you know, Oklahoma is not bad, but you know, who came up with Michigan? You know, Maryland, you know, how did those borders get made? Well, those are the same people that did the constellation borders. You know, why so many zigs and zags? Why can't they be more square-ish? But anyway, the International Astronomical Union, IAU, in the early 1930s, put 88 constellation boundaries together for the 88 constellations that we recognize worldwide from the International Astronomical Union. Again, different cultures may have their own versions, and that's fine, but as so many things need to be standardized worldwide, like the metric system, except in the United States, you know, worldwide standards are helpful. And the 88 constellations is a worldwide standard, though some cultures make up their own stuff, which is fine. So you see the Great Square of Pegasus is 3 stars in Pegasus, but 1 star borrowed from Andromeda. And the name of that star is Alpheratz. It's the brightest star in the Great Square of Pegasus. And the way I remember that name, I just think of a huge rat, the alpha rat, Alpheratz. And the Great Square of Pegasus is what? An asterism. It's not a constellation. It's a familiar shape made up of stars from 2 different constellations. But we have Andromeda itself, which I'll show you in the theater for part 2, and Pegasus I'll show you when we get into the theater. So Orion is a winter constellation, but it's very popular, and people, even though it's summertime, would ask me, can we see Orion? And the answer is, well, you really can't because the sun's in the way, though Orion is emerging in the very early skies now. But in any case, I just use this to illustrate naming of stars. So we have Betelgeuse, the upper lefts, which you can tell is reddish in color. And we have Rigel, as we look at it, the bottom right, which is bluish in color. And we name them with Greek letters. So interestingly enough, in the night sky, the Arabs named most of the stars. The Greeks and Romans came up with most of the constellations, and the stars have Arabic names, most of them, the brighter ones, but Greek letter designations to make it easy for all of us. Yeah. So Betelgeuse is Alpha, is the alpha star, and Rigel is the beta star, though there's debate of which one's brighter, and most people these days are feeling that Rigel is actually brighter than Betelgeuse. So technically, Rigel should be the alpha star, but it's, back when these things were originally done, it was like naked eye. It looks like, and you may or may not realize that a couple of years ago, we had a significant dimming of Betelgeuse, where it really dimmed and people were concerned, and there was hype about, is it going to blow up? Well, no. Stars don't dim when they're going to blow up, they get brighter. But in any case, so we've got alpha, beta, gamma, according to their relative brightness in general. And Betelgeuse would be called Alpha Orionis, Rigel, Beta Orionis, Gamma Orionis, the upper right star, etc. So that's one way that stars are named. And then, as I mentioned to you, many stars have Arabic names, and there's a couple of stars that I will show you when we get into the theater where to find them in the constellation of Libra. So here's a couple of names that I just love to say. Would you like to say them with me? Of course you would. Okay, so the top name is Zubin Eshamali. Can you say that? Zubin Eshamali? Good. And then the bottom one is Zubin el-Ganubi. Zubin el-Ganubi. And these are the two brightest stars in the constellation of Libra, the scales. And Zubin means claw. And Eshamali means northern. And el-Ganubi means southern. So we have here in Libra the northern claw and the southern claw of what? The scorpion, who's to the left. Antares is the heart of the scorpion. So that's another story for another time. Somebody cut off the claws of the scorpion. Who would do such a thing? Julius Caesar. Okay, so I'll mention Antares again later, but Antares is the heart of the scorpion. And so here are some more Arabic names. These are the names of the stars in the Big Dipper. Is the Big Dipper a constellation? No. It's an asterism. Okay, see, and I didn't even have the word up there. Okay, good job. So Alkaid I mentioned. How many light years away is that one? 100. That's your century star. Alkaid's 100 light years away. Then we have, why is there two names there? Mizar and Alcor. And if you look carefully, you can see there's two stars there. And the reason there's two stars there is because there's two stars there. And if you take time to observe, and that's one of the problems that is with our generation, the next generation, the younger generation, we got to get back to our video games. We don't take time to observe and appreciate. How many of you have, in fact, gone out and looked at the middle star of the handle of the Big Dipper and noticed there's two stars there? 1, 2, maybe. Do that. That's your assignment tonight, if it's clear, and it's 50-50 whether it will be or not. But the next clear night, Big Dipper is always up, depending on the time of night is where it will be. And I'll show you where it will be in part 2 when we go into the theater. You folks at home, remember, come to a show, 3 o'clock, it's the night sky. Pardon me? So you go out, the brighter star that you see, that everybody sees, that's Mizar or Mizar. And the dimmer one, which if you take a little time, dark sky, you just can't come out to your kitchen door and look up and say, oh, I can't see it. You got to give your eyes time to get adjusted to the darkness. And then you'll look, oh my goodness, Dave was right. There are two stars there, Mizar and Alcor, not to be confused with Al Gore. Okay. And then Alioth, Megrez, Bekta, that's a hard one for me to say, Mirak and Dubi or Dubé. These are the 2 pointer stars, Mirak and Dubé. I'll show you later when we get into the theater how to find the North Star. So again, Arabic names, because you got to remember, back 4,000 years ago, back in Babylon, Mesopotamia, Iran, Iraq, Baghdad was a cradle of astronomy. Back then, they had to watch TV by candlelight. So what do? You go out and you know what you do with clouds, right? When there's a nice puffy cumulus clouds out there. Oh, that looks like a dolphin. Oh, there's an elephant on the back of a turtle. Uh-oh, here comes the lion eating the turtle. We play those with, and so what did they do? They didn't have cribbage games then either, you know? You would go out at night, no light pollution, no air pollution. Go out, look at the night sky, and what do you see? I see a big bear. Ah, the brightest star. Let's name the stars. Okay, any questions so far? The next slide is a little on the complex side, so there will be a quiz, so you want to pay attention. But any questions anybody would like to ask, any chats at home or anybody here on anything I've shared with you so far? Everybody's good? Okay, I'm just going to pause for a quick drink. Because the next slide is going to take a little time. Because remember, I'm teaching you now about the sky. What are some of the metrics that we use to describe and talk about the night sky? Then we'll go into planetarium theater and we'll look at where this stuff is. So, the Hertzsprung-Russell diagram, a staple of all good college astronomy students. So let me just explain briefly how this works. There's two axes. There's the y-axis, which is vertical. The x-axis is horizontal. Along the y-axis is brightness. How bright are things? A brightness of 1 is equivalent to the brightness of our star, the sun. That's what we define it as, okay? Then we go up, 10 to the first, 10 to the second, 10 to the third, 10 to the fourth is 10,000 times brighter than our sun. And going the other way, down 10 to the minus second is 100th. Stars that are 100th as bright as our sun. Along the bottom, we have temperatures. 30,000, 20,000, 10, 5,000, 3,000, 2,000, measured in Kelvin. Okay, Kelvin is the absolute temperature scale, where 0 Kelvin is absolute 0, where all molecular motion ceases. So on that scale, to the left are the hotter, or the hottest stars, 30,000 Kelvin. To the right, a mere 2,000 Kelvin are the cooler stars. Our sun is here, pretty much in the middle, at about 5,600 Kelvin. 5,600, luminosity of 1 is our sun. So you can see to the right are cooler, to the left are hotter, going up are brighter, coming down are dimmer, okay? And another time we can talk about, well, what does this main sequence mean? It has to do with the life sequence of the birth, death, and life of stars. Another time, okay? Any questions? So colors come into play here. So the cooler stars are red, the coolest being red dwarfs. Okay. Then there are white dwarfs, which are hotter. And we'll talk about those another time. Our sun is yellowish. And then we have the blue giants, hot, very, very luminous stars to the upper left. The hotter stars of blue lie to the left, and the upper ones are the biggest. So this diagram, we can get all kinds of information from. Question anybody wants to ask about this diagram? Okay, remember there's a quiz. Okay, most stars are found along the main sequence. So what do the colors mean in English? Well, we're used to, in our cars, like now, Where's the blue? I can't get enough blue. Crank it up to the blue. Why? That's air conditioning. In the wintertime, I need more red. I need hot. I need heat. Well, in nature, it's the other way around. The red stars are the cooler ones. The blue stars are the hotter ones. What color flame were you told to have in your chemistry lab? Blue, right? Once your Bunsen burner flame, blue. Why? It burned the hottest and the cleanest. You don't want a yellow flame. Yellow flames are cool. You don't want to put your hand on it. But relative to what you might need to bend or mold glass, a yellow flame isn't going to do the trick. So red stars are the coolest, around 3,000 Kelvin. Orange stars, right? You take a horseshoe, you put it on the anvil. Well, before you put it on the anvil, you put it in the furnace, pump up those bellows, and that horseshoe glows red hot. Get more air in there, it's going to burn, it's going to turn orange. I can get enough air in there now, it's going to turn yellow, because yellow is hotter than orange. We're in the realm now of about 5,500 Kelvin, about the temperature of our sun. And then, I don't know if we got enough, now we have to get some oxygen to pump on the fire, but if I can get some more oxygen into the flame, I can get my horseshoe to turn white hot. You've heard that term, white hot. How hot was it? It was white hot. That's hot. But then there's blue hot, and we're talking beyond 30,000 Kelvin. Any questions about the temperature? So here are some examples of some stars, which I will show you in the planetarium theater. Red star, like Arcturus. I will show you where to find Arcturus. Antares is another one. I'll show you where to find Antares. An orange star, a little warmer, Aldebaran. It's in Taurus, it's a winter constellation, but it's making an appearance in the early morning sky. Yellow stars, like our sun, they're pretty average. Capella is an example of a yellow star. Our sun is a yellow star. White stars are really hot. Mintaka is in the belt of Orion, and that's a good example of a white, pure white star. Blue-white stars, like Spica. You can maybe catch Spica before it sets now. It's an late spring, early summer star. And then blue star, I already mentioned to you, Rigel, bottom right star in Orion, is an example of a really hot star. Vega overhead, we'll talk about, is a bluish white star, really hot and really, really bright. Questions about color? We're going to move on to how bright things are. So that's about color. Questions about color? Red to blue? Yes.
Why is red is like more of a flaming color? Why is it the other way around in nature?
Well, if you were in a laboratory and you had your burner on, okay, it's hard to get a red flame unless you put something like strontium in the flame. But it's the first color you're probably going to see is yellow. Okay? But as you add more oxygen, more air, the flame gets hotter. It goes from orange to yellow to white and then blue-white. Okay. Good question. And sometimes it's hard to explain, well, that's the way it really is in nature. Who made up the dial on the car? Why do they put red dots in a hotel on the hut? Somebody just decided, probably, because you look at a fire and the glowing embers and it's hot. Okay, so we're going to talk about the magnitude scale. This has to do with the brightness of stars, okay? So this was first introduced by a guy named Hipparchus around 127 BC. And he was Greek. And what are Greeks famous for as you think of athletic competition? The Olympics, yes. The Greeks, big on athletic competition. And what was one of the big events, one of the first early events?
The Olympics.
Yes, what event in the Olympics? Huh? What do you think? Running, yeah, running, marathon, running. Yeah. So who's the winner? What place does the winner get? First. And the next one in gets what place?
Second.
Second. Good job. So this guy Hipparchus thought, we're going to do the same thing with stars. The brightest stars will be first place stars. The next brightest stars will be second place stars. And then he and his buddies decided, well, I mean, how far are we going to go? I mean, you could have 100 runners in a race, and well, who comes in 100th? But they decided, we'll go top 6. So a 6th magnitude was the limit of human visibility. Okay, so decided and agreed upon, and to this day, it's agreed upon that magnitude 6 is the limit on a dark, clear, air pollution-free, light pollution-free night. You can see a magnitude 6 with average eyesight. Some people can see dimmer, some people not quite, but on average. Okay, so now Hipparchus is sitting around with his buddies and says, okay, good job, we've got this down. First, second, third, fourth, fifth, and sixth place stars. How much brighter do you think a first place star is than a sixth place star? And they sat around and, you know, chit-chatted around. And of course, remember, they don't have any quantifying instrumentation. They're just using their eyes. And they're just, oh, there's a bright star and there's the dim one. I think it's about 100 times brighter. And so that was accepted. Magnitude 1 star was 100 times brighter than a magnitude 6 star. And so if you're into math, I'm a math teacher also, and we just actually talked about this in my Algebra 2 class, how to do this, but you've got 5 divisions from 1 to 6. There's 5 divisions. You want them to be equal, so the first one times the second one times the third one times the fourth times the fifth is going to give you the sixth, and that's the 5th root of 100. So get out your calculator. What's the 5th root of 100? 2.512. So a magnitude 1 star is 2.512, or we can say 2.5 times brighter than a magnitude 2 star. A magnitude 2 star is 2.5 times brighter than a magnitude 3 star, etc. And a magnitude 1 star is 100 times brighter than a magnitude 6 star. And that lasted for many, 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 many years. And Hipparchus had a stamp made out, a Greek stamp. And drachma, there's a delta and a rho. 2. I'm not sure, 2.50 drachmas. I don't know what that equivalent to, but a long time ago, it was worth something. But anyway, so now we come into the 18th, 19th century, and now we're building electronic equipment that we can actually measure how bright things are. We've got light meters for cameras, and as time goes on, they become, like now, I can't even tell you how sensitive things can be. But there came a point where, oh, we can actually measure this. Okay, so there's a magnitude 6 star. Okay, we got a number. Bingo. Good, 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 good. There's a magnitude 1 star. Okay, how bright's that? Oh, it's a lot brighter than 100 times. So because of modern technology, they decided to keep this 5th root of 100. They thought that was good. We're going to keep that scale. They thought faintest magnitude 6, that's good. We're going to keep that. But we've got the problem with these brighter stars. So we're now going to go from magnitude 1 to magnitude 0. So a magnitude 0 is going to be 2.5 times brighter than a magnitude 1. And we got Sirius. I'm serious. Brightest star in the night sky in either hemisphere. It's out in the winter. Negative 1.42, negative 1.44 magnitude. We got planets. Jupiter now is at a negative 2.7. It's going to be a negative 2.8 soon. Venus is a negative 3.9. The moon, oh my goodness, we could go on. So you know what? Let's go on. Sirius, negative 1.42. We have a full moon at about a negative 12. We have the sun. We didn't measure the daughter, but the sun, okay, is about a negative 26.5. So we now have a way to quantify the brightness. And what we're talking about here is apparent brightness, how things appear to be. There's also what's called absolute brightness. Right? How bright really is that star compared to our sun or something else? That's another topic for another time. Absolute magnitude, different topic. We're talking about apparent magnitude. Okay, so here are some stars. Polaris, the North Star, is a magnitude 2. Alpheratz, that I showed you, in Andromeda, right, is a magnitude 2. Spica, Antares, Deneb, are all visible now, particularly Antares, the heart of the scorpion. Deneb overhead is the tail of the swan. They're magnitude 1 stars. Arcturus, Vega, Capella, they're magnitude 0 stars. They're 2.5 times brighter. Sirius, negative 1.42, brightest sky in the night sky. Jupiter, negative 2.8, mid-August. Saturn, 0.5. Venus, negative 3.9. There are times when it gets to negative 4 point something. Mars, about a 0.5 this month. So that's how the brightness scales work, how we talk about the brightness of objects. Questions? Everybody good? Brightness? Okay, awesome. So let's talk about the celestial sphere. How do we orient ourselves? Now we know about a little bit about distances. We know something about what the color of the stars mean. And again, you have to take time to observe. You just can't go out your kitchen door, look up, and they all look white to me. Take some time and notice, oh yeah, that does look orange. That one looks even redder than that one. That one's definitely white. That one has a little bluish tinge to it. Take time to observe, and you'll see the colors pop. And the brightness is pretty easy to tell that that's happening. So here are some things. Directly overhead is what's called the zenith. Used to be a TV. Underneath your feet, like on the other side of the world, if you will, like, you know, we used to talk about digging down to China, is what's called the nadir, or the nadir. We have our globe. And most globes, when you buy them, they're on a stand, and the stand has the globe tilted at 23.5 degrees. Not straight up and down, but 23.5 degrees, because that's the way Earth is tilted for real in space. And the North Pole, or the rotational axis of Earth, points to the North Star, almost. The North Star is actually 3/4 of a degree off dead center, but close enough for state work. Chuckles? Then we have the equator on Earth. The celestial equator is a projection of the equator on Earth up into the sky. And if I could use, and sorry if I step out of your field of view for a minute, but if we could look at the projector as the sun, and here I am, the autumnal equinox is coming, right, in September. So this is the autumnal, or the September, the fall equinox here. The rotational axis of Earth keeps pointing that way, like above the exit sun. When we come over here, for us in the northern hemisphere in New Hampshire, now we're in winter. We come over here to the vernal equinox, and the light from the sun is hitting the equator again. And then we come over here, I won't trip over the cord. And now you can see the tilt of Earth is pointing towards the sun, and that's why we have summer and so warm in the summertime, is because the rays from the sun are so direct on Earth. So Earth goes around the sun, the axis of rotation is always pointing in the same direction. Avez-vous une question? Okay. So, some important terms to keep in mind because they affect other things. So, if we were looking at the North Star here, and again, technically it's 3/4 of a degree off dead center right now, it's going to get within a 1/2 degree in the year 2100. So we have the Little Dipper coming around. We have the Big Dipper on the right side of your screen, and looking down, notice it rotates counterclockwise. And so Ursa Major will go up, go overhead, and come down and such. And I'm going to show you in the theater how this happens. It's a great illustration. You're going to love it. So we'll have a 10-minute break when we're done here shortly, and then meet in the theater and see all the magic of what we've talked about here. So the sun is in the center. Earth orbits the sun in a counterclockwise fashion. And then realize that wherever Earth is, when we look at the sun, and don't look at the sun, even sunglasses, you need the eclipse glasses, which we'll have in our shop soon.
I looked at the sun with sunglasses on.
I didn't need to know that. But if you could vision, like in January, looking towards the sun, we see Sagittarius, because we can't see Sagittarius in the winter time. Why? Because the sun's in the way. So now we are in July, we're over here, right? January, March, June, July, so we're over here. And if we were to look at the sun, which we're not going to do, right? If we're over here, Earth is here. If we could look towards the sun, we would see the constellation Gemini, which we can't see because the sun is in the way. So looking in the opposite direction at nighttime, right? In January, we look away from the sun sets, we look away from the sun, we see Gemini. As we move into spring, we look away from the sun, now we can see the constellation Cancer. Now in July, we look away from the sun at night, and we see Sagittarius. Okay, make sense? Soon it'll make dollars. Okay. And etc. So, due to Earth's revolution around the sun appears to move through the zodiacal constellations, which is the sun's apparent path in the sky. We call it the ecliptic. That's a good word to remember, the ecliptic. And the ecliptic is the projection of Earth's orbit onto the celestial sphere. So for example, here, we see this line is the ecliptic. It's the path of Earth around the sun, but since we're on Earth, it appears to be the path of the sun through the sky. So the sun goes through Pisces, Aries, Taurus, Gemini, Cancer, Leo. Those are the signs of the zodiac. Not going to get deep into it now, but there's a 13th constellation of the zodiac, maybe you know, Ophiuchus. The sun actually spends 3 times longer in Ophiuchus than it does in Scorpius. But somebody forgot about that. So some things I'll show you in the theater. When we go in there, I'll show you the Zubins, Zubin Eshamali, Zubin El-Ganubi. I'll show you where to find a couple of double stars. I'll show you the Ring Nebula, which is very far away. It's in the constellation of Lyra or Lyra. I'll show you the summer triangle, which is an asterism of stars, not in one, not in two, but in 3 different constellations. Can you believe it? Doesn't get any better than that. I'll show you the summer triangle. M13, Messier object number 13 on Charles Messier's list, is in Hercules. It's a great cluster of stars, and you can kind of see a fuzzy spot, naked eye, binoculars. It's like, oh wow. And tonight, if the astronomers are here, you may be able to see that. Interestingly enough, I thought I'd put this in just for trivia. July 4th is when Earth is farthest from the sun. And around January 4th is when Earth is closest to the sun.
What?
Yeah, I know. Isn't that true? You want to know something? The answer is yes. You want to know something? Yeah. So maybe you saw, you can look this up. It's an old video, Harvard graduates. Okay, people just graduated from Harvard. Somebody with their VHS camera interviewed. Some of them still have their caps and gowns on. What causes the seasons? The answer by Harvard graduates, well, how far away the Earth is from sun. When is the sun closest to Earth? In the summer. When is it furthest away? In the winter. We're talking, Boston, Cambridge, Northern Hemisphere. And that's their answer. And it has nothing to do with how close to Earth it is. It has to do with what I told you before. It has to do with the tilt of Earth's axis and where Earth is in its orbit around the sun. That's what causes the seasons. It has nothing to do with the distance of Earth from the sun. But don't ask a Harvard graduate that question. And I'll show you, oh my goodness, it's coming right up and we're going to be done. How big are these things? Well, here's the sun. Again, we don't know what the daughter is. Here's Earth. You can see Earth. Folks there at home see Earth. The arrow's pointing to Earth. That's how big Earth is compared to the sun. You can fit 109 Earths across the face of the sun. You can fit 1.3 million Earths inside the sun. 1 1/3 million Earths inside the sun. It's big. That's big. Jupiter, our biggest planet, Pluto, our smallest planet, yes, Pluto's a planet, don't get me going. So Pluto's a pixel here. Earth is about 9 pixels, and Jupiter's pretty big, biggest planet. It's 11 times larger than Earth. You can fit 11 Earths across the face of Jupiter. We're about 8,000 mile diameter. Jupiter's about 88,000 mile diameter. So now let's look at some of the stars we've been talking about. Here's our sun now. Jupiter is now 1 pixel in size. Sirius, the brightest star, is this big, so significantly bigger than the sun. Oh my goodness, Pollux, one of the twin stars that you can't see right now because it's in Gemini. Castor and Pollux, the twins. Oh my goodness, look at the sun compared to a star called Arcturus, which I'm going to show you in the theater, which you can go out at night and you can see it with your own eyes.
It's huge.
So it's huge. It's a magnitude 0 star and it's red. Let's stop there. Oh, I got another button. You ready for this? Okay. Here's Arcturus we were just talking about. Our sun is now 1 pixel. Rigel, Aldebaran. Here's Betelgeuse, the upper left star in Orion, compared to our sun. But that, you ain't seen nothing yet. Well, I guess you can. That's behind my head. Antares. That I'm going to show you in the planetarium theater where to find it. You can see it outside tonight, maybe, depending upon where the trees are. Antares. You know how big Antares is? And that's where you say, no, Dave, how big is Antares?
Yeah.
If we were to put our sun, which is now 1 pixel, at the center of Antares, the orbit of Mars would be inside that star. It is humongous. So that's a little bit about size. How far are things? Well, we went through the bit, so I'm not going to bring that slide up again. We talked about the Big Dipper in some detail about distance, but how far is this galaxy, the Andromeda Galaxy? Here's Cassiopeia, which I'll show you where to find in the Planetarium Theater, and the acute angle, right? You remember obtuse angles are bigger than 90 degrees. Our acute angles are less than 90 degrees. The acute angle, as an arrow, points to the Andromeda Galaxy, which is a fuzzy spot, which you can make out with the unaided eye. Binoculars, there it is. Telescopes, unbelievable. It's there. How far away is that? Remember I told you about light years? Right? 7.5 times is the speed of light. Light traveling for 1 year at that speed is a light year. Well, how about 2.5 million light years away? Traveling that fast, traveling 186,282 miles per second. It's going to take 2.5 million years to get to Andromeda. And I'm going to show you this. Guess where? In the theater, yes. After these messages. So, yeah, that's what I got to show you here. Hope that was helpful. And you can write me at astromannh@gmail.com, and I would be happy to answer your questions. So, let me ask if you have, we got a few more minutes here. Let me ask you if you have, I'm just trying to get my clock going here. Questions about anything. It can be related to what I talked about, or maybe you just thought of something else that's unrelated to what I talked about, but it's on your mind.
Okay, what channel can we watch the show on?
That's a great question. It's my show and I don't know what channel it's on. So it's on Concord Cable TV. I think there are three channels, and I'm not sure which one it is. But if you Google or you go to YouTube and search The Sky This Month, Dave McDonald, because somebody else plagiarized my name. So there's others, The Sky This Month's out there. I'm Dave McDonald. So The Sky This Month, Dave McDonald is my show. And I can make that available, so, or if you write me, I can send it back to you. Because I'm going to be sending out the YouTube link tonight, actually, because like I said, it just got published today. Good question, and thank you for that question. Other questions? Yes, sir.
Do all stars start their night as bright, and then as they leave, that's right?
Oh. There's a star party at Hobbs Cook State Park in Maine. The last weekend in August. I think it's August 25, 26, 27, or it might be 26, 27, 28. But the last weekend at Hobbs Cook State Park. And on Saturday afternoon at 1 o'clock, I'm going to be presenting about the stellar graveyard, the birth and death of stars. So come on up. It's only 6.5 hours from here. So I showed you that main sequence. So stars are born as material, gas and dust, come together and gravitationally become attractive, and nuclear fusion ignites. And it depends on how much material there is as to how bright it's going to be, how long, how large the star is going to be, how long it's going to last. Interestingly enough, larger stars, you might think, well, they have more fuel, but larger stars burn out more quickly. They have a higher nuclear furnace, so to speak, going on, and they're going to burn through more elements. our star, the sun, is burning hydrogen, changing it to helium, and we're gonna burn some helium, and then we're done. And then we're gonna go nova, we're gonna end up as a red dwarf. 5 billion years from now, but you can put on your calendar.
It's still being made.
Oh my gosh, yes. You need to tune into my show. And you need to hear Kelly Beatty, who's the senior editor of Sky and Telescope magazine. And we're gonna talk, part of the talk will be about the James Webb Space Telescope and finding places where stars are being born. And we can see them being born now with this technology. We've been aware for years with the Hubble Space Telescope, the pillars of creation, you can look that up as in the Orion Nebula is a birthplace of stars. So yes, stars are being formed and born continuously, yes. Yes.
I was wondering, have you watched the show Nova?
Say it again, please.
Have you watched the show Nova?
Nova, you wanna know something that you're gonna love? I have a Yorkshire Terrorizer, a dog, and guess what her name is? Nova. But yes, I love Nova. I have a lot of Nova shows that I show to my astronomy class.
It's my favorite. It's the only one.
It's a great show.
Did you see the one with the Milky Way that was on last week? Wasn't that cool?
Did you see the one with the Snickers?
I watched the one where the whole universe was being born.
Neat.
Best one on Earth.
And
Big Bang.
you know what? The James Webb Space Telescope is going to be looking as far back as we can, further back than Hubble could. Towards, we can't see the Big Bang because there's a period of what's called darkness. There's what's the Dark Ages, which was about 380,000 years long. But we hope to see first light of stars, first light of galaxies with the James Webb Space Telescope. Other thoughts, questions? Perfect timing, it's 8 o'clock, and at 8:10, we'll have a 10-minute intermission, and at 8:10, we'll open the doors to the theater. Come on in and I'll show you the grandeur of the skies and the stuff that we talked about. I'll show you where to find it. Sound good?
Yes.
Okay. Thank you for your kind attention, and hope to see you in the theater in 10 minutes. Thank you for joining us at home. Don't forget, 3 o'clock, The Sky this month is a TV show. Tonight's Sky is the name of the planetarium show, 3 o'clock every day here at the McAuliffe-Shepard Discovery Center. You want to be sure you come in and check it out so you can see where the stuff I've talked about can be found. Thanks for joining us. I'm Dave McDonald.